Today we are going to talk about the principle of mathematical induction, and it's a pretty similar process to, in methods how you guys did the derivative from first principles. It's a real sort of long methodical process like that, and it's going to be very exciting. We're going to jump back to sort of series a bit, and we remember we've got this series here, we've got 1 plus 2 plus 3 plus all the way up to n, okay? And so the claim here is that for any value of n, okay, be it the first 3 terms or the first 15 terms, that the sum of all of them is equal to this formula, n times n plus 1 over 2. Okay, so first, let's just test it to see if it works for a few cases. So if we think of p of 1, so that means I'm using n is 1. I'm saying the sum of one term. Okay, if I've got p of 1, the first term is 1. Okay, so if we consider this equation, the left-hand side is 1. Okay, we've only got one term. Okay, so the p of 1, the left-hand side is 1. And what about, so I've written it up here as well, the left-hand side is 1. What about the right-hand side? That's going to be 1 times, the value of n is 1. 1 times 1 plus 1 divided by 2 is 2 divided by 2 is 1. So it's true when n is 1. Okay? I'm just going to demonstrate a couple more. What about if we were to check 3? Let's check it for 3 terms. So then on the left-hand side, we're going to have 1 plus 2 plus 3. Okay, so the left-hand side is 1 plus 2 plus 3, which is 6. All right? And the right-hand side is going to be 3, the value of n is 3, times 3 plus 1 divided by 2. Okay, so that's 3 times 4, which is 12, divided by 2 is 6. So it works for 3 as well. We've got 2 cases here to suppose it is true. So we're going to do some clever maths, all right? What we're doing is we're thinking of it like a line of dominoes, okay? What we've seen is the first domino falls over. It works in the first circumstance, okay? Our question is going to be if we can get these dominoes to fall over. Okay? If we can get them to fall over, then we know it's going to work for the whole sequence. So the way we're going to set it out, we always need to remember state. We need to state the thing we're testing. We need to test it. And we always test it for the lowest case, the very first domino. Okay? In our circumstance here, our first domino is 1. We're told this is valid for n is greater than or equal to 1. Okay? If it says n is greater than or equal to 0, then our lowest domino is 0. We're going to test it for the case 0. I did 3 up here just to illustrate to you that it works for another number as well. So I'm going to rub that out now. We've performed the first test. Okay? And we've seen that p of 1 is true, and so that's going to be our statement. Therefore, p of 1 is true. The first domino falls over. Okay. Then what we're going to do is we're going to say, let's jump ahead. So here's the first domino, here's the second domino, here's the domino. Here is the nth domino. Okay? And we want to say, is it true for all of these dominoes? Now, somewhere in between here and here, we're going to have a k domino. Okay, somewhere between 1 and n. And the domino that comes after the k domino is going to be the k plus 1 domino. And so what we're going to do, we're going to say, we're going to assume it works for k. And if it works for k, does it work for k plus 1? Okay, so let's go ahead and do that first. And then I can maybe come back and point to the dominoes and point out the relationship there. So we've got p of 1 is true. The first domino is true. So let's make the assumption. If p of k is true, okay? If p of k is true, if it's true for some number between 1 and n, if it's true for k, so that means 1, 2, 3, all the way up to k. Okay? If p of k is true, it means 1 plus 2 plus 3 plus all the way up to k, okay? Somewhere between 1 and n, all the way up to k, is equal to k times k plus 1 on top of 2. Okay? If it's true, so all we've done is restated this, but in terms of k. Okay, we're not proving the thing, we're proving k. If P of K is true, then this is P of K. I'll write that up here as well. The series of K. All right, so then we're going to prove it. I'll move this down a little bit. So we've made our test, we've stated our assumption, now we're ready to prove it. If we are going to say, what is P of K plus 1? Let's write out the whole series. It's going to be 1 plus 2 plus 3. Let's make this statement first. P of K plus 1 equals 1 plus 2 plus 3 plus K plus K plus 1. Okay? So we're assuming P of K is true. That's what P of K would be. And then we're going, well, what about P of K plus 1? The one following. So notice how it's got P of K, and then plus the next term is going to be K plus 1. Okay. Is that okay so far? All right, cool. So then let's do a clever substitution. Look at this. This here is what? This is this whole thing. This whole thing is P of K. P of K is 1 plus 2 plus 3 all the way up to K. And that's what this statement is here, 1 plus 2 plus 3, all the way up to K. And then we have plus K plus 1. Now we have made the assumption that P of K is true. So that means P of K equals this, is equal to this. So because we're making the assumption, we can perform the substitution from there, here for P of K. So we've got P of K plus 1 is K times K plus 1 on top of 2, plus K plus 1. Okay, so let's break that down a bit more. Here's P of K, the statement for P of K. We're assuming it equals that. Here's the statement for P of K plus 1. And we can see it incorporates the P of K statement. And so we're performing that substitution. Now we're going to mash these together. Okay, so before we can mash them together, we need this to have the same denominator. So we could write that as 2 times K plus 1 on top of 2. Now they have the same denominator, now we can add them together. So that's going to be K squared plus K. And then over here we're going to have 2K plus 2. All on top of 2, okay? I've combined those two together. Let's simplify a little bit more. We're going to have K squared plus 3K plus 2 on top of 2. Okay? We can factorize this expression, and we've got K plus 1 times K plus 2. Okay, that's using the cross product method. If we factorize that, we're looking for two numbers that multiply together to give us 2, so 1 and 2, and add together to give us positive 3. So let's look at that. Let's look at that a little bit more slowly. We substituted in P of K. There they are. That's the K plus 1th term. This is P of K, the whole series of P of K. We're adding them together, collecting like terms, and then we factorize. Okay, so that's P of K plus 1 in its most simple form. Is it true? Based on our formula here, okay, this is for the K term. What about if we say, what is P of K plus 1 according to our hypothesis? This is what we're testing. If we substitute K plus 1 in here, what have we got? We're going to have K plus 1, okay, that's going there. And then we're going to have in brackets K plus 1 plus 1 divided by 2. Okay, which is K plus 1 times K plus 2 on top of 2. So, we've proved it, okay? And our last step is to explain. We're going to say, because P of 1 is true. Okay, we've got P of 1 is true. And P of K plus 1 is true if P of K is true. Therefore, P of N is true. for NEZ. NEZ plus. Okay, let me explain that. So I've made the statement, let me explain the explanation. Think of these dominoes, okay? We've tested this one, okay? We've said it works for the first case. And then we've said, okay, what about, we want to know, is it going to work for all of them? Well, let's jump ahead to some domino K. And let's say, we're going to assume this domino falls over. We're assuming this domino falls over. And we're saying, if this domino falls over, this one will this one fall over? Okay, that's what we're doing. We're saying this one definitely falls over. Does P of K plus 1 also fall over? We see that when we substitute K plus 1 in here, and when we substitute K plus 1 in here, we generate the same answer. So it holds true for K plus 1. So what that means is if this one falls over, this one definitely falls over. Okay? That's revolutionary, because what that means is every domino that follows is going to fall over. We've proved this one falls over, and by our proof that K plus 1 falls over, we've proved this falls over, it means this has to fall over. Okay? That's what we proved here. If this one falls over, this one will fall over. Well, this one's fallen over, which means this one will fall. And then we apply the same logic. Well, if this one falls, we know the next one's going to fall. And so we know it holds for the whole sequence. Okay, it's pretty hard. It's pretty hard, so we're going to go through a number together. I'm going to go through one more up here by myself, and then there's two that we will go through together. So I'll spin it around, and we'll just get started again.
Triangle.
First up here is the sum of all odd numbers. And this one's maybe a little bit easier, you might think. So let's make the statement state. Okay? P of n, the sequence the series that we're testing, is the sum of all odd numbers. The nth odd number is equal to n squared. Okay, we've made the statement. All right, that's the statement. Let's test it. Let's test and see if it's true. Now we always test for the lowest value of n. Here it's stated again for n being greater than or equal to 0. Greater than or equal to 1. Most of them are 1. Okay, so we're going to test it. First we're going to test the left-hand side. Okay, if we take the first odd number on the left-hand side, first positive odd number is 1. Okay, how about the right-hand side? We put our value of n is 1, we put 1 in there, we're going to have 1 squared, which is 1. Okay, therefore, P of 1 is true. The first domino falls over. Okay, so we've established our test case. It works in our test case. Let's make our assumption. We're going to assume that P of K is true. Okay, so P of K is going to be somewhere in between 1 and n. So it's going to be 1 plus 3 plus 5 plus k. It's the kth odd term. And if P of k is true, then it equals k squared. Okay, so I need that because it's an assumption. If P of k is true, then P of k equals k squared. Okay, how about k plus 1? Like if we're thinking, now we're on to our test case, our proof, sorry, proof. So we've got state, test, assume, prove. P of k plus 1. Okay, so if we're doing all of the odd terms, all right, we're going to have 1 plus 3 plus 5 plus k. Now, sorry. Sorry, this is supposed to be 2n take 1, and so that means this is 2k take 1, and this is 2k take 1. Let me explain why that's the case. 2k take 1, we're saying for any value of k, that's the kth odd term. All right, so if you think 1, 3, 5, this is the third odd term. 5 is the third odd term, right? And so if you go 2 times 3, take 1, that's 5. Okay? What about the fourth odd term? 2 times 5 is 8, take 1 is 7. So that formula there is going to be for the kth odd term. It's not just k like it was previously, it's very low. Okay, so we have plus 2, 2k take 1. So that's p of k. And then we're saying, well, what about p of k plus 1? So we've got all the way up to k, and then plus, we need to substitute k plus 1 in here. Okay? And if we're performing that, here we've got p of k, and here we've got the k plus 1th term. And if it is true, if p of k plus 1 is true, then it's going to equal k plus 1 squared, isn't it? Okay, if k plus 1, if it's true for the k plus 1 term, then it's going to equal k plus 1 squared. So this is what we're trying to prove. We're trying to prove it's equal to p of k plus 1. Let's go from the left-hand side. Here, this whole statement is the p of k statement that we're assuming is true. That whole thing is p of k. Alright? That's the p of k statement. And so then what we've got, well, what are we assuming p of k is? K squared. So that whole thing substitutes to k squared. So if we continue the expression, we've got k squared and then plus this here. I'm going to extend that out. We're going to have 2k plus 2 take 1. Okay, let's process it a bit more. We can select those like terms there. That's going to be k squared plus 2k plus 1. And we can factorise it to be k plus 1 squared. Okay, so what we've shown here is if p of k is true, then p of k plus 1 is also true. The left-hand side is equal to the right-hand side. And so then we explain. Okay, and we're always making the same statement for the explanation. Okay, because p of 1 is true, and p of k plus 1 is true whenever, or if p of k is true, then p of n is true for n is a positive integer. Okay, remember z is the set of integers, the plus at the top denotes positive, so for n being 1, 2, 3, 4. Okay, very good. So maybe that one, maybe we're starting to see it a little bit. We're going to do 2 together now. So if you turn the page, first one we've got there is the sum of each integer squared. So I'll clear some board space. Okay, so this one says, and I might go over two spaces here to something I might big enough. We've got 1 squared plus 2 squared plus 3 squared plus n squared. Okay, so the sum of each integer squared is equal to n times n plus 1 times 2n plus 1 on 6. Okay, that's the statement we need to make. So where it says p of n, okay, you need to restate what p of n is. That's the very first line. P of n, we're writing that statement. So then we're ready to test. Okay, that's what we're doing in the next step. We're testing the left-hand side. If we're saying n is 1, we're taking the first term on the left-hand side, it's going to be 1 squared, which is 1. How about on the right-hand side? If we put n is 1 into the right-hand side, Okay, we're going to have 1 times 2 times 3 divided by 6 is 6 on 6 is 1. So we've got the left-hand side is equal to the right-hand side. Therefore, P of 1 is true. Okay, so they've made the statement for you, and most of them start a bit structured like this, just to get you in the habit of setting it out. Therefore, P of 1 is true. Okay, we've tested. Let's make the assumption about P of K. Test, assume. Okay, all you have to do in this step, okay, is restate exactly what you have here, but with K instead of N. All right, assume P of K equals 1 plus 2, 1 squared plus 2 squared, plus 3 squared, plus all the way up to K squared. Okay, so if P of K is true, then this is going to equal this. Okay, so then I'm saying, I'm making the P of K plus 1 statement. This is what we're trying to prove. We're trying to prove that P of K plus 1 is equal to when we substitute K plus 1 into P of N. Now I'm going to simplify this statement here just so I can get a good idea of the direction we're aiming, that we're trying to manipulate this towards. So the first term stays and remains as K plus 1. This goes to K plus 2. And this is going to go to 2K plus 2 plus 1. This goes to 2K plus 3. Okay, anyone unsure how I generated this? Alright, so we're substituting K plus 1 over here. Okay, so then this is what we're trying to prove. So let's process the left-hand side. Okay, that's what we're going to start with, and we're going to manipulate what we've got here until it matches what we have over here. Okay, if we can't get it to match, then it means it's not true. If we can get it to match, then it means it is true. So P of K plus 1, let's have a look, and we're always going to do that substitution with these problems. Okay, we should always have P of K stated there. That is P of K. All right, and what are we assuming P of K is? We're assuming P of K is this. And so that's the substitution that we're going to perform for P of K. We're going to have K times K plus 1 times 2K plus 1 on top of 6 plus K plus 1 squared. Okay, so I've performed that substitution for P of K plus 1. Okay, so now we've got to mash them together. So before we can do that, they need to have the same denominator. So 6 and 6, we can do that straight away. They have the same denominator, so what that means, I'll make the statement here, but you won't necessarily need to write this out. K plus 1 times 2K plus 1 plus 6 times K plus 1 squared on top of 6. So let's look at the direction we're trying to go, right? This is what we're trying to get it to equal. We're going to try and write it like that. And so you can see we've got the 6 at the bottom, that's fine. There's a number of ways you can do it. If you were to expand everything and then factorize it, that would generate an answer, but it's a cubic, so it'd be very difficult to factorize. Instead, what we're going to do is I'm going to look along the top here. We've got 2 terms at the top, and we can see one factor that is common to both terms. K plus 1, isn't it? It belongs to this term and it belongs to this term. And if we pull it out the front, look what's out the front of the expression here, k plus 1. So that's a good way to start. We're going to look at that when we go, we need to pull that k plus 1 out the front. And if we do that, what are we left with in brackets? Well, here we're going to have k times 2k plus 1. Okay, I've pulled that out, so we've gotten rid of that one. We're left with that. And then plus, here we're going to have 6 times k plus 1. All on top of 6. Okay. Now let's perform the expansion there, because we can factorise a quadratic quite easily. So we're going to expand both of them and bring them together. This k plus 1, that's just going to hang out the front for now. And I'm maybe just going to whack the 6 there, so I don't have to write the 6 every time as well. So we've got k plus 1 on 6. I'm going to have 2k squared plus k plus 6k plus 6. All right, I'm going to, in the next step, collect like terms. And then I'm ready to factorise. Okay. Where are we stuck? Fred?
I don't understand how you went from the heap of the K's out the front there.
That one?
Yeah.
Yep. So here I'm looking at these two terms, and I'm thinking that belongs to this term, and k plus 1 belongs to that term. So it's common to both. So if I pull it out the front, we've got that big bracket there. I've removed it. If I were to expand it again, it's going to belong to that term, and then we're going to get the square there as well.
Yeah.
So that's how we pulled that one out.
Yeah.
And I've pulled the 1 on 6 out as well, just to make it a bit easier. Expanded, collected, factorised, and this is the exact same as what we predicted k plus 1 would be if it is true. Okay, so we've performed the test, we've made our assumption, we've proved that it's true if the assumption is true. So then we explain. Okay, is it filled in at the bottom for you? Yeah. Okay, so it's if, because P1 is true, okay, it's true for the first domino, and then we're saying we've proved as well that it's going to fall. So if I draw those dominoes up again, we know it's true for this one, and then we've proved for any value of k, if it's true here, then it has to be true here. So we can move that pattern anywhere along here and know that it's going to be true for any value of n. Very good. Okay, one more to sort of maybe have a go at. You guys have a bit of a go at, and I can write an answer up here.
Solution.